In this video, we will explore the concept of black body. The radiation generated by hot objects was known practically since humans controlled the fire. However, the invention of the incandescent bulb started the great revolution of physics, in terms of new capabilities to perform experiments involving light. Also, it generated a huge interest on the explanation of the radiation generated by the light bulb, because a successful model could generate better ways of fabrication, and consequently better profits. But, in order to generate a successful theory, it was important to understand the process quite well. It is important to mention that the radiation spectrum generated by a light bulb had a very specific signature. Notice how the vertical axis represents intensity, while the horizontal axis is put in terms of wavelength. In this sense, let's take a moment to think of the meaning of using wavelength in the graph. Actually, when we refer to wavelength, we mean that a wave is generated. Moreover, the generated wave is light. And yes, although obvious, the light bulb generated light. Then, when we talk about the radiation spectrum, we refer to the set of wavelengths generated by the device. On the other hand, something less obvious is to find what are the characteristics of the radiation spectrum. Let's suppose a piece of iron getting out of a furnace. It glows orange-reddish color, as well it emits a huge amount of heat. Also, magma flowing out of a volcano generates a very similar color, as well as heat. Finally, if we observe a barbecue, we could see that also the burning coal generates a reddish color, and obviously, heat. What could be the reason for this behavior? Now, if we measure the radiation spectrum of each of these cases, we found that they are actually very similar. But, the important fact is that although the materials are different, the radiation spectrum is practically the same. On the other hand, a model commonly used for the study of radiating objects is known as a black body. A black body is an ideal object that perfectly absorbs and emits electromagnetic radiation. But, what can be considered a black body? Although the answer could sound weird, actually, any hot body can be modeled, to a certain extent, as a black body. For example, a light bulb, a human body, and even a star can be a black body. Also, the radiation spectrum depends only on the temperature of the body. But the most important fact to remember is that the material and shape of the black body do not affect the radiation spectrum. Then, we can say that in our previous example, iron, magma, and coal can be assumed as black bodies. If we return to the original question, what are the characteristics of the emitted light by a black body? We find the following common characteristics. All black bodies emit exactly the same spectrum when at same temperature. Their radiation spectrum is continuous. Increasing the temperature increases the radiated intensity at all wavelengths. And increasing the temperature causes the peak intensity to shift toward shorter wavelengths. These effects can be seen in any radiation spectrum generated by a hot body. In the following graph, it can be seen the characteristics previously described. Could you identify each of them? On the other hand, empirical models to describe the radiation spectrum of a blackbody were developed along the years, but they did not explain the origin of the radiation spectrum. Two models were particularly successful: the Wien's and Stefan's laws. Wilhelm Wien proposed the displacement law, that later was called the Wien's displacement law, and predicts the wavelength at which the maximum intensity should appear. Its explicit expression was set as follows: with lambda the position at the maximum intensity, and T the temperature. A second empirical model was called the Stefan's law after Joseph Stefan. It refers to the total power of blackbody radiation, emitted across the entire spectrum at a given temperature. The Stefan's law has the following expression: Stefan's law is sometimes written in a similar way as the Wien's law as follows: where P is the emitted power, T the temperature, and A the surface area of the body. In some textbooks, the Stefan's law includes an efficiency factor called emissivity. Although mentioned before, it is important to remember that these models did not explain the origin of the radiation spectrum. They were proposed based on experimental data. Let's solve an example to see how the Wien's law works. Example 8. Determine the temperature of the filament of a light bulb if its peak intensity is at near-infrared light with wavelength of 870 nanometers. Could you solve it? Answer. We know that the Wien's law has the following form. Also, the peak intensity is located at 870 nanometers. Then, solving the Wien's law for the temperature, we see this. Substituting the wavelength into this equation, we see the following. Then, we find that the temperature of such a filament should be 3331 Kelvin degrees. It is clear from this example that the temperature is not enough to center the radiation spectrum in the visible range. Actually, only a small fraction, about 10%, of the energy delivered is located in the visible range. Most of the energy is lost as heat. Then, a natural question should be: what is the heat we can feel with our skin? The answer to this is not as simple as one could imagine. Actually, the heat as we experience is another way of electromagnetic radiation, but its wavelength is too long to be seen by our eyes. For example, if you put your hand near a stove at 100 Celsius degrees, you could have a quite painful experience. Well, the heat you sense in such a case is non-visible light with wavelength of 7.7 micrometers. Finally, a human body, with an average temperature of 36 Celsius degrees emits radiation with wavelength of 10 micrometers. Moreover, each human emits about 100 watts of power. Actually, the military-grade night vision goggles use this wavelength to search in the darkness. In the next video, we will study the Planck's model that explain the origin of the black body radiation. Stay tuned.